We're going to look at extreme points of polyhedra in standard form. A polyhedron in standard form is one that can be described as a set of x in Rn such that Ax is equal to b, x is greater than or equal to 0, where A is an m by n matrix with full row rank, that means all the rows are linearly independent, and B is an m vector. There are a couple of reasons why we want to look at polyhedra in standard form. The first is historical. Polyhedra in standard form are the kind of polyhedra that people look at when they study linear programming. The second is, as we'll see, there is something convenient about using polyhedra in standard form. The first thing I want to point out is a fact. If this set P is non-empty, then P has an extreme point. Well, this fact of course requires proof, and I encourage you to think about it and come up with your own proof. But now we're going to look at characterization of extreme points of polyhedra in standard form. So let's pick an extreme point x star. And by a previous theorem, we know that if we look at all the constraints satisfied with equality by x star, when we take those, set them to equality, they will give us a unique solution. Then x star is the unique solution to the following system. Well, obviously x star has to satisfy Ax equal to b with equality, and then we have these constraints where n is a set of indices j such that xj star is equal to 0. Let's look at this system more closely. We are setting xj to 0 for all j in n. So basically, we can knock out all the xj variables in this system up here. So if my a is, say, like this, so say my a is like this, and say n is 2 and 3. So if we set x2 to 0 and x3 to 0, the first column times x1 must be equal to the right hand side b. What this means is we can write this equivalently as follows. Summing over all indices not in n, the jth column of A times the jth variable has to be equal to the right hand side b. And this system is going to have a unique solution. What this means is if j is a set of indices not in n, then the submatrix A formed from taking the columns indexed by j has linearly independent columns. Or in other words, A sub j has full column rank. Alright, now notice that since rank of A is m, this set j cannot have more than m elements. So right away we can say that at least n minus m components must be 0. It turns out that we can go the other way, and here's what I mean. Let's take a set j to be a subset of the indices of the variables with j as most m, and suppose that A sub j has full column rank. Then if x star greater than 0 is such that aj x star j equal to b and xj star equal to 0, where j is not in n, then x star is an j not in j, then x star is an extreme point of P. Right? Because this is same as the saying that x star satisfy Ax star equal to b and xj star equal to 0 for all j not in j. And so x star is a point in P that is uniquely defined by this system. So if we write this system as Ax equal to b, xj equal to 0, where j is not in J, then this has a unique solution, and x star is the unique solution. So x star is the extreme point of P. What have we got? If you want to find extreme points in P, all you have to do is find at most m linearly independent columns in A. Let's say the indices of those columns give you the set J. Solve this system, and if all the components are non-negative, you have got an extreme point. And all extreme points arise this way.